Uh, in this series of problems, we are again playing with sets which are measurable as well as sets with finite outer measure, and how to approximate them by open sets, closed sets, or intersection of open sets, countable intersection of open sets, or countable union of closed sets, what we call G delta and F sigma sets. Okay, it's very interesting that we do not go beyond. We do not go beyond in this kind of approximations. We do not go beyond the G delta and the F sigma. In fact, we will see later on when we deal with measurable functions that we do go beyond that. But in any case, here, so let's start with the first one. So we have a set which is measurable. So A, we want to show that A is measurable if and only if for every epsilon, okay, there exists uh, C closed and O open such that C is smaller than A, smaller than O, and the outer measure of O minus C is less than epsilon. So for that, we need the characterization that we have learned before in that about measurable sets. So we know that, okay, we know that A is measurable if and only if for every epsilon, okay, there exists C closed, okay, in A such that the measure, the outer measure A minus C is less than epsilon, and there exists O, which contains A open, such that the outer measure of O minus A is less than epsilon. So if we consider O minus C, it's very easy to check that this is O minus A union A minus C, which implies by the properties of the outer measure that the outer measure of O minus C is less or equal than outer measure of O minus A plus the outer measure of A minus C, okay, which is going to be less than 2 epsilon. So if A is measurable, then we are done. Okay? So assume now, for the converse, assume that for every epsilon, okay, there exists C closed and O open such that C is included in A included in O, and the outer measure of O minus C is less than epsilon. So in this case, we know, obviously, since it's just properties of the set theory, so we know that O minus A is a subset of O minus C, which implies that the outer measure of O minus A is going to be less or equal than the outer measure of O minus C less than epsilon. And again, by the characterization that we know, A will be what? Measurable. So A is measurable. For the second one, we have a subset A of R with its outer measure, which is finite. Okay? So what we want is to find a G delta. So let us prove there exists a G delta, let's call it G, which contains A, such that the outer measure of G is equal to the outer measure of A. Okay? And in order to do that, we know by definition of the outer measure. So now let's go back to the definition of the outer measure. So for every epsilon, we can find O, let's call it epsilon, open such that A is included in O epsilon, and the outer measure of O epsilon is less than the outer measure of A plus epsilon. Yeah? So keep in mind, the outer measure of A is finite. Therefore, this is finite. So the outer measures of every open O epsilon is finite. Okay? So now let's take O. Let us take O to be the intersection of the one that corresponds to 1 over n. Okay? Okay, so this is a G delta, since it is a countable intersection of open sets. We know that A is in every O epsilon, therefore it is in O. And we know also by monotonicity is going to be, okay, M star. The outer measure of A is going to be less or equal than the outer measure of O, which is less than the outer measure of every ON, because O is a subset of O 1 over n, which is less than the outer measure of A plus 1 over n for all n greater than 1. And obviously, this will imply what? That the outer measure of O is equal to the outer measure of A, okay? By letting n go to infinity. The second part is interesting because it claims that, or it asks us to show that A is measurable if and only if we can find F, an F sigma, such that F is included in A and the outer measure of A is equal to the outer measure of F. Okay? So, okay, so first, let us prove that if we assume, okay, assume that there exists an F, which is an F sigma, such that F is in A and the outer measure of A is equal to the outer measure of F. Okay? And let us prove that A is measurable. So, what do we have? Since F is measurable, okay, it's an F sigma, it's a Brillouin set, so F is measurable. Okay, by definition of the measurability, we know that the outer measure of A is going to be the outer measure of F intersect. It's true, but let us write it correctly, and then A intersect F plus the outer measure of A intersect F complement. Okay? So the A intersect F is equal to F because F is a subset of A, and so this will imply that the outer measure of A is equal to the outer measure of F plus the outer measure of A intersect F complement, or the difference set between A and F. So since the outer measure of F and the outer measure of A are equal, we get, and finite, very important, then otherwise it's not true. We get that the outer measure of A intersect F complement is 0. This is very important, the fact that the outer measure, okay, since yeah, the outer measure of A is finite. Okay? If it's not, this may be a problem. Okay? So this will imply that, so since it has an outer measure which is 0, then A intersect F complement is measurable. Okay? So F union A intersect F complement is measurable because F is measurable and the union of two measurable sets is measurable, which tells us that A is measurable. Okay? Uh, Now assume that A is measurable. So we know that there exists an F sigma such that F is included in A and the outer measure of A minus F is equal to 0. So the concise equality gives us, since F is measurable, that out, the outer measure of A minus F, because F is a subset of A, and F is measurable, is equal to this minus the outer measure of F. And this implies, obviously, that the outer measure of A is equal to the outer measure of F. So we use the fact that F is measurable. Huh? So to go from here to here, we use the fact that F is measurable. The last problem, okay, so we are starting with, for 3, let A be a subset of R such that the outer measure of A is finite. So we know that if A is measurable, if and only if, so we know that A is measurable if and only if, for every epsilon, there exists an open set such that A is in O and the outer measure of O minus A is less than epsilon. Okay? Great. So assume that A is not measurable. Then there exists an epsilon 0, okay, such that for any open set which with A included in O, then we have the outer measure of O minus A, which is greater than epsilon 0. Okay? On the other hand, by definition of the outer measure of A, we know for this epsilon 0, there exists an open set, open, such that A is a subset of this open set O0, and the outer measure of O0 is less than the outer measure of A plus epsilon 0 over 2. Any number less than epsilon 0 will do, as you will see. So this will give us that the outer measure of O0 minus the outer measure of A will be less than epsilon 0 over 2. Yeah? And we said for any open set which contains A, okay, this will be less than epsilon 0, less or equal than O0 minus A, which implies that the outer measure of O0 minus the outer measure of A is less than the outer measure of O0 minus A. Okay? So this will complete the proof of the third question.